Next speaker is Jahan Claes from Yale, and it's going to talk about high threshold quantum error correction for Rydberg atoms with biased erasures.
Okay. Okay. Hi, everyone. Thanks for having me, and thanks to the organizers for organizing this very nice workshop. So today I'm going to be talking about some work on new ways to do quantum computing with Rydberg atoms and why these ways might be superior to some other approaches just because of the structure of the errors in this approach. Before I kind of okay. So before I get into this work, I want to acknowledge my collaborators. I'm going to be, shamelessly presenting on work that was done by lots of other people as well. So at Yale, there was Ruthie and Kavya who did a lot of this work. And we're also closely collaborating with Jeff Thompson's group at Princeton, who is the person who actually understands Rydberg atoms and has the devices that he can actually test some of these ideas on. So, and we're also building on previous work by Shruti and Jeff and some other people. So to start, I want to kind of lay out what the take-home message of this talk is going to be. And there's a general theme of the research on error correction at Yale, which is that some sources of error are much harder to correct than other sources of error. So when people talk about quantum error correction, they often talk about depolarizing noise. Just at any given time, your qubit could experience an X error, a Y error, a Z error. You won't know about it, and you'll have to correct it at some later point in your computation. A few years ago, it was realized that actually biased Pauli errors, where most of the Pauli noise comes from a single Pauli operator, like the Z operator, is easier to correct than depolarizing Pauli errors. Even further to the right on the scale are erasure errors. And erasure errors are like Pauli errors, except they happen at known locations. You can detect when they occur. And this knowledge of their location makes them even easier to correct. And what I'm going to be talking about in this talk is a kind of new error model that we've introduced that's inspired by the particular Rydberg atoms we're working with. We're calling it biased erasures. So these metastable neutral atoms we're going to be looking at have a particular error channel that I'll explain in a second. And this error channel is even easier to correct than erasure errors. And so given this error channel, we're going to introduce new schemes to correct these biased erasure errors that have drastically higher thresholds, meaning that we can tolerate a lot more of these errors and still be able to perform a computation reliably. So our thresholds can be as high as 17%, meaning that for every 2-qubit gate, we can have a 17% chance of having a biased erasure, and we can still correct our errors. This should be in contrast to depolarizing errors, which are way at the other end of the scale, where the threshold is around 1%. Your 2-qubit gate error has to succeed more than 99% of the time if you want to be able to reliably perform quantum computation. And so the big picture takeaway you should have, even if you don't care about Rydberg atoms in particular, is that if you understand the sources of noise in your device and tailor the way you do error correction, you can improve your error correction a lot. And in particular, the fidelity of a 2-qubit gate is not the only relevant metric. The source of that infidelity is also very important. Okay, so let's get down to the specifics of the system we're going to be studying. So this is a very simplified energy diagram of ytterbium-171. And it has a lot of energy levels, but we're going to ignore most of them. It has this ground state manifold. There's actually multiple states down here, and you can encode a qubit down here if you want to. And this is an approach that's been used in the past. But it also has this metastable energy levels over here. And we're going to choose to encode our qubit in this metastable energy level. The fact that we're encoding a qubit in this metastable energy level does have some downsides. In particular, this metastable energy level can decay to the ground state. So that's an additional error channel that we wouldn't have to worry about if we encoded our qubit down here. On the other hand, we're going to see that the fact that our qubit is encoded in the metastable energy level means that we can detect most of the errors. So if this qubit decays to this ground state, we can simply image the population of the ground state non-destructively and detect that, oh, an error has occurred. So if we kind of continually image whether or not we're in the ground state, we can always know if this error happened. To understand and fully appreciate the structure of these errors on these metastable qubits, we have to understand how we do entangling gates, because the entangling gates are going to be the dominant source of errors. These qubits have very, very good coherence times if you just leave them alone. But if you try and do a 2-qubit gate to them, this is where the problem starts. So the general approach to entangling these neutral atom qubits is based on the Rydberg blockade. So we're going to drive this transition from our qubit subspace into a very highly excited state called the Rydberg state. And in particular, we're only going to drive the 1 state to this Rydberg state. The 0 state, we're going to apply a pulse that doesn't do anything to the 0 state. And if we do this, and there's 2 atoms that we're doing it to that are close together, if one atom goes to the Rydberg state, it doesn't really do anything to this atom. But it does prevent the other atom from going to the Rydberg state. So we can't have 2 excitations at once. This is just because of dipole-dipole interactions. These Rydberg states just are very large. The electron cloud is kind of blown up. And so it has a wider radius of interactions. So the overall kind of thing that happens when you drive these transitions is that, okay, if you're in the 0-0 state, you just stay in the 0-0 state throughout this pulse. If you're in the 0-1 state, you can be excited to the 0R state because you're driving this 1R transition. And then we bring you back down to 0-1. And we do this so that you don't accumulate any phase. We choose this path so you don't accumulate a phase. And similarly for the 1-0 state. But if you're in the 1-1 state, we're driving to this state that's a superposition of R1 and 1R. And we can simply choose this pulse so that this other path that we're driving along, we accumulate a phase along that path. And apologies, this should be -1, 1 down here. You're accumulating a phase as you come back to yourself. So the overall pulse then applies a CZ gate by populating this highly excited Rydberg level. And that's going to be the entangling gate we play. So now we can try and understand what are the errors going to look like during this entangling gate. Well, it so happens that the dominant error, as you might expect, happens while you're in this hugely excited state. When you're in this highly excited Rydberg state, your decay rate is much larger than kind of any other decay rate in your system. So the dominant error is a decay from the Rydberg state while you're populating it. And in particular, you almost always decay to the ground state down here. You don't decay back into your qubit subspace very often. And what this means is that if we do this 2-qubit gate and then measure the population of the ground state, we can know whether this error happened or not. And finally, and this is very important, this is kind of the unique feature of this gate, is that we know that the Rydberg state would only ever get populated if we started in the 1 state. Which means the ground state will only ever get populated if we had been in the 1 state. Overall, we can say that detecting a decay, detecting population in the ground state is like accidentally measuring your qubit as being in the state 1. The qubit's now gone. You've kind of destructively measured the qubit to be in 1. So if we think about an erasure happening during a CZ gate, what this looks like is, okay, I detect, oh no, an erasure has happened on one of these qubits. Then what should I do? I should replace that qubit, obviously, because I need to refresh the qubit if an erasure happened to continue my computation. But I shouldn't just replace it with a qubit in a random state. I should replace it with a qubit in the 1 state, because that's somehow going to make sure I don't destroy all of the information that I have. I've measured that qubit in the 1 state, I replaced it in the 1 state, and then the overall error channel that we get is looks like we accidentally measured in the Z basis. So it's this kind of something that looks like depolarizing noise. We have an equal chance of being in our original state and being in the state where we applied a Z error. But it's not really depolarizing noise because we only apply Z errors. We don't apply X or Y errors. There's no probability of an X or Y error. Because if you accidentally measure a qubit in the Z basis, you've destroyed information about the X operator or the Y operator, but you've preserved your information about the Z operator. Accidentally measuring the qubit in the Z basis means that you can later come back and measure the qubit in the Z basis again, and you haven't destroyed anything. During a CX gate, the errors are a little bit different, because to do a CX gate, what we're going to do is we're going to Hadamard a CZ gate. And so that Hadamard obviously converts Z errors to X errors. So a CZ gate has a slightly different structure of errors. If an erasure happens on the top rail, it's just the 1/2 probability of applying a Z error. But if an erasure happens on the bottom rail, and we do the same thing, we'll have a 1/2 chance of applying an X error. But in either case, we know exactly what poly error happened. We know it's either an X error or Z error whenever we detect an erasure. So importantly, if we have biased erasures, that means we know which qubit had the errors. We get this little flag that says, oh no, this qubit was erased. And we know what poly error might have happened to that qubit. So this is a lot of information. So now that we have this information, we should go up to the next level and think about how is this information going to be used in error correction. So I just want to give a very brief overview of quantum error correction with the surface code. And I'm going to present the XZZX surface code because it has some nice properties. So hopefully everybody has seen the surface code before, but the basic idea is that at every vertex in this lattice, we place a qubit, and then we repeatedly measure stabilizers to detect errors. And the stabilizers we measure look like XZZX, hence the name. And if we don't have any errors, these stabilizers are always supposed to give us back 1. But if we have errors, then they'll give back different outcomes. And then we have a Z logical operator that kind of goes across the top of the surface code and an X logical operator that goes along the boundary. And so if you just check an X error on any qubit is going to anti-commute. It's going to flip the values of the stabilizers above and below. So we'll catch X errors by seeing minus signs above and below that X error. And similarly, we catch Z errors by seeing minus signs to the left and right of that error, because it flips those stabilizers. The XZZX code is kind of interesting because for biased poly noise, it has a very high threshold. So if you mostly have Z errors instead of just kind of uniformly Z, X, and Y errors, then what happens is easier to figure out where the errors occurred, because you know the Z errors only create these minus signs kind of to the left and right, which means you have a lower dimensional decoding problem when you're trying to go from these minus signs to figuring out where the errors are. And so this has been known, since this nice paper in 2021, that if you look at the XZZX code and you increase the bias, you increase the ratio of the Z errors to the other errors, the threshold goes up by quite a lot. Well, if you have kind of other surface codes that don't have this nice low dimensional decoding structure, increasing the bias doesn't really help. So that's all I want to say about the XZZX surface code. So why does the structure of biased erasures help us correct errors? Well, if we just think about poly errors versus erasure errors, we can already see that erasure errors are going to be easier to correct than poly errors. Because, for example, if we don't know where the errors occurred, then if, say, 2 X errors occur here and here, all I see are these minus signs. And I have to guess where the errors were based on the minus signs. And I might guess that actually the X errors occurred there and there. And I'm totally wrong and I've caused a logical error. So 2 poly errors can totally screw me up for this piece of surface code. On the other hand, if I know where the errors occurred, I get a little more information. So if I get these erasure flags that tell me these 2 qubits were erased, and then I replace them with fresh qubits and I measure the stabilizers again, then maybe I measure the same pattern of minus signs, because maybe when I measure the stabilizers again, it turns out that my replaced qubits had an X error compared to my original qubits. But in this case, I'm not confused at all. I'm not going to say, oh, well, maybe there was an X error up here and an X error down here. I know where the X errors occurred. And so I'm going to successfully figure out what my errors were. And so here, 2 errors are correctable, just because you know where the errors occur. Biased erasures are going to be even easier to crack. Why are biased erasures going to be even easier to crack? Well, if I detect a normal erasure at some qubit, and then I replace it with a fresh qubit, when I measure my stabilizers, I have an equal chance of measuring an X error having happened, a Z error having happened, or a Y error having happened. And I have to figure out which of those happened based on the pattern of minus signs I see. On the other hand, biased erasures, I know exactly what poly error I'm going to get. So there's no step of the decoding procedure where I look at the minus signs and try and deduce what poly error occurred. I know where it occurred and I know what occurred. So if I see a biased erasure here, and I know it's going to be a Z error, then I have a lot more information that I can feed my decoder when it's trying to figure out where these errors occurred based on the minus signs. So we can start by just saying how good is our error correction if we just run a circuit to measure the stabilizers of the XZZX surface code. So if I want to measure one of these stabilizers, I'll use an ancilla qubit and I'll entangle it with the 4 data qubits using these entangling gates. I'll use CZ and CX gates because I have to measure XZZX. And if I ever see an erasure, then I'll just replace the erased qubits with fresh qubits that are initialized in 1 from some reservoir that I can bring in. And we'll define this RE fraction is the fraction of the errors that are biased erasures. So I'm not going to assume that literally all my errors are biased erasures, but I'm going to assume that most of them are. And then the remaining errors are just going to be random depolarizing poly errors that I don't know about. So we can just do simulations and figure out what the threshold is. And if we just use a circuit to do error correction, we get a threshold of 10.3% if everything is biased erasures. And if we do a more realistic simulation where we assume, say, 98% of our error sources are biased erasures and 2% are poly errors, which we think is going to be achievable in some next generation of experiments, then we have a threshold of 8.2%. And I just want to compare this to some previous work on unbiased erasures, where you could have X, Y, or Z poly errors. And there, the numbers are roughly half what we're getting. And this should all be compared to about 1% for pure poly depolarizing noise, which is happening at R equals 0. Okay, so I want to take a step back. This is all fine. This is a good argument for just doing normal surface code error correction with these Rydberg atoms because they have a nice error structure. And I want to understand, why is the XZZX surface code good at correcting these errors? And in particular, is it good at correcting biased erasures for the same reason it's good at correcting biased poly noise? They both have biased in the name. And the answer is no, it's not. Biased poly noise, you have a high threshold because your decoding graph is lower dimensional. Z errors only create these minus signs to the left and right. On the other hand, these biased erasures, remember, we're using these control not gates. And these control not gates, when you have an erasure, it can introduce X errors. A control Z gate, when you have an erasure, it can introduce Z errors. So there's no sense in which we're just only getting X errors or only getting Z errors in our XZZX surface code. The reason this is good at correcting these errors is just because of the reasons we went through on the previous slides. We know where the erasures occurred, and we know what kind of poly errors can occur at those locations. And we're using all of that information when we're trying to figure out where the errors occurred. And it's not because our decoding graph is somehow low dimensional. But that does raise the question, is there some other strategy for decoding where we can do all of the things we previously did? We use the information of the locations, we use the information about what kind of poly errors occur, but we also get a low dimensional decoding graph. And could this push our thresholds even higher? And the general idea is we want to avoid using control not gates because control not gates introduce X errors. And we know the XZZX surface code is particularly good at correcting Z errors. So we're going to try and efficiently realize XZZX error correction without ever using a control not gate. And we're going to do that using measurement-based quantum computation. So I want to pause here and just check my time. Yeah, I want to pause here and just introduce the idea of measurement-based quantum computation. Measurement-based quantum computation is built around this idea of a cluster state. And cluster states, we draw them using sticks and balls. A filled ball is an X-type qubit. What that means is it's a qubit that's prepared in the plus state. And if we ever measure it, we measure it in the X basis. Open ball is a Z-type qubit. So we prepare it in 0, we measure it in Z. And then if I connect them with a line, that means we apply an entangling gate between them. And the type of entangling gate we apply depends on the types of qubits we connect. So we either apply CX or CZ gates, depending on what types of qubits we're connecting. And the particular graph we're going to draw has this unit cell down here. So I'm going to kind of build up the graph. It's going to look a little complicated, but just remember it's this unit cell. So if we just kind of tile things, we just keep going. We put the unit cells next to each other. And this is the cluster state that our error correction is built around. And the idea behind the cluster state is if we put an XZZX surface code state in one end of it, and then measure all of the qubits but the last layer in the X or Z basis. What that does is it teleports the surface code state to those qubits in a way that is robust to errors. So it's doing quantum error correction by teleportation. And the way we check for errors is it turns out that this state, if there's no errors in it, the measurement outcomes around the faces of any unit cell are supposed to multiply to 1. So this ZXXXXZ measurement outcome is supposed to multiply to 1. And so in particular, if there's, say, a Z error here, we would measure that the stabilizers centered at these unit cells would give us -1 and tell us that there was a Z error there. And similarly, if there was a Z error at that qubit, there'd be minus signs, kind of into and out of the page. And if there's an X error on that qubit, there'd be minus signs above and below. The nice thing about this cluster state, the way I've drawn it, is that if we have Z errors only, it has the same property as the XZZX surface code, which is that if we have Z errors only, we reduce the dimensionality of the decoding problem, because X errors are what cause minus signs to occur up and down. Z errors just occur left and right and kind of into and out of the cluster state. So we want to generate this cluster state, and I've drawn this picture, but you'll notice that the recipe I've given you involves using CX gates. So that's no good, because we want to avoid using CX gates. And the strategy we're going to use is we're going to prepare small entangled states, and maybe we'll use CX gates during this preparation, maybe we won't. I don't care, because we're going to prepare these small entangled states and post-select on no erasures. So these small entangled states are not going to have any of these biased erasures with X errors in them. And then we're going to join them into larger entangled states using some combination of control Z gates, which we're allowed to use, and multi-qubit measurements. And we're going to optimize this construction to have the same probability of biased erasures per measurement cycle to make sure that we have a fighting chance of outperforming the circuit-based model. And the overall strategy we're going to use is that multi-qubit Pauli measurements can be used to join qubits into the larger cluster state without ever using controlled NOT gates. So it turns out that if we measure XX on 2 of these qubits that are not entangled with each other, measuring XX on 2 qubits projects you into a 2-dimensional subspace. You did have a 4-dimensional subspace because you had 2 qubits. This is going to project you into a 2-dimensional subspace. And that joins you into a single effective qubit. And this measurement actually preserves all the previous entanglement you had. So you now have an effective single qubit that's entangled with all of these qubits. And it has some effective Z operator and some effective X operator. And then if you want to measure out this qubit, because remember, to do the error correction, we actually measure out these Z-type qubits in the Z basis. We actually want to perform the 2-qubit measurement Z1, Z2, because that's the effective Z operator. So overall, we want to just measure XX and measure ZZ. And we can do that with this nice little circuit down here, where we use an ancilla qubit and control Z gates to use this ancilla to measure Z1, Z2, and then use direct single qubit measurements to measure X1, X2. Importantly, if an erasure happens, we can modify the circuit so we still get the Z1, Z2 information. If an erasure happens here, say, we've destroyed our X information. So we're no longer going to get X1, X2 information. But if we just switch these measurements to be Z measurements, we've preserved the Z information this whole time, because biased erasures preserve Z information. So we can still extract Z1 times Z2. And so what that looks like is we don't get to know the XX measurement outcome, which determines some Pauli corrections we need to apply to our state. But we do know the ZZ measurement outcome. And this is going to maintain the symmetry of this cluster state. So in the few minutes I have left, I'm just going to outline how we actually construct this large entangled state and then show you some thresholds. So step 1 is we prepare small entangled states. We're going to prepare these with control NOT gates, but it doesn't matter because we're going to post-select on no erasures having happened. And so we can try, many, many times and take the successful ones and drag them into position. Then we line up all of these little resource states into a 2-dimensional plane. And we're going to create a 2-dimensional cluster state by fusing these X-type qubits with XX measurements. And then we're going to get effectively this 2-dimensional plane of qubits that we've made without ever having kind of unpost-selected control NOT gates. And then finally, this is a 2-dimensional cluster state. We needed a 3-dimensional cluster state to do error correction. So we take a bunch of these sheets and stack them on top of each other. And then we can directly entangle them with control Z gates. because we're allowed to use Control-Z gates. And we finally get the whole cluster state that's going to do error correction by teleportation. So this is a little bit involved, a little bit convoluted, but the idea is we're trying to have the same number of errors, but in a way that makes the errors arranged nicely so we can correct them even better. And if we just do this numerically, what we see is that the XZZX cluster state, if we have all biased erasures, we get a threshold of 17.7% against these erasures, which is probably the highest threshold against any sort of error under circuit level noise. If we kind of go to a more realistic regime of having the 98% biased erasures, we still have a threshold of 10.3%. So we're beating the surface code in both cases. It's a little bit more involved to realize it, but in both cases, we can correct more errors. And this is because we're successfully taking advantage of information on the location of errors, knowledge of the types of poly errors, and we're building in a low dimensional decoding graph. We're kind of bringing every single possible tool to bear on correcting these in the best possible way. And I just want to flash that, okay, recently there have been some preliminary work showing that we can do this erasure detection. Right now we're at 33% of the errors come from these biased erasures. And there's some data that shows that they really are biased. They only occur from the 1-1 state. They don't occur from the 0-0 state. But there's reasons to believe that this number is going to get much better in the future. This is just preliminary data from Jeff Thompson's group. And with that, I'll conclude and take any questions.
There's been some work in the photonics community showing that when you have erasure errors, you could even go beyond 50% thresholds. Could you maybe compare your results with those?
Yeah, absolutely. So, so we were kind of trying to use the smallest possible resource state to kind of put a minimum burden on this post-selection step. So in general, what you should think, though, is that any heralded error, any error that you know when it happens, you can have almost arbitrarily high thresholds to this error simply by using larger and larger resource. I mean, the photonics community is also doing cluster state stuff. So they're taking these resource states, and then they're joining the resource states together, and they're preparing the resource states in some sort of very noisy way, but post-selecting on having no noise, and then joining them into larger cluster states. So if you're sure that the only source of error is this heralded error, then, and you only care about thresholds, you don't care about actual practical overheads, what you should do is you should create really huge resource states that you only succeed with probability 0.00001% of the time or something. But you try to make them many times. And then on the successful ones, you have these large chunks of entangled state that have no errors, they're perfectly pure. And then you just sew them together on the boundaries with some entangling gates. And the only source of error are these like boundaries. And so you can have thresholds well in excess of 50% if you use this strategy, but with the caveat that these resource states that you're just kind of saying, oh, I'm going to prepare them by post-selection, you almost never get them. You have to have some insane overhead on just preparing the resource states. So for this work too, if I chose larger resource states that weren't just these 8-qubit resource states, but instead chose 100-qubit resource states, I'm sure I could push this threshold over 50%. But the caveats are, first off, this doesn't help you against poly errors. This only helps you against the biased erasure errors. And at some point, you just run out of the number of qubits in your device. It takes a long time to get these resource states.
So, yeah, over here. Sorry. Yes. Now, in the situation where you have heavily biased errors on your physical qubits, do you think maybe using a surface code is like too much? You're providing too much protection, given some finite resources, and you'd be better off, using a set of codes that use far fewer qubits, like small concatenations with 7-qubit codes or something.
Yeah, I think that's an interesting question, especially for the Rydberg atoms, because I think one of Jeff Thompson's goals is to have like kind of a fully reconfigurable device where you can drag any pair of qubits next to each other. And then you can really start looking at these concatenated codes that don't have nice locality properties, but maybe have nice other properties. I think our general point of view is that if you have highly biased noise, there's probably, I mean, you could do a repetition code, which just corrects against one type of error, or you could just kind of do a very thin surface code that kind of corrects against X errors and really corrects against Z errors. And this is kind of where we're imagining the future is, where you just say, oh, I don't have to correct against very many X errors. So I kind of squish the direction of the code that's correcting against X errors. And you can do that with this cluster state. You can make one direction of the cluster state squished. You can't do it with this circuit-based error correction because, like I said, we have kind of equal X and Z errors because of these biased erasures.
Last question.
I have a problem is that in your calculation for the threshold for the second scheme,
Yeah.
you use into account like the fact that you have an overhead for preparing this resource states.
Yeah, absolutely. So the fact that we have an overhead for preparing these resource states doesn't actually affect the thresholds if we're in the regime of R equals 1. So if there's all biased erasures, because in that regime, the resource states are perfect. But when we're looking at all of these data points at lower R's, we're taking into account the fact that when we build these resource states, we're accumulating poly errors. We're accumulating more poly errors than the circuit model, in fact, which is why this curve kind of drops faster than the circuit model as we increase the number of poly errors. But yeah, we're taking that into account in our simulations. So these resource states have poly errors, and we put them in, and then they get new poly errors and also biased erasure errors.
Hey, thanks for